Hello everyone, my name is GND from the Research Center for Information Technology Innovation, Academy Sinica, Taipei, Taiwan. I will present my research is about dopamine transporter SPECT image classification for neurodegenerative Parkinsonism via diffusion maps and machine learning classifiers. In our research, we make three major contributions in this paper. First is dimensional reduction. Our study proposed a nonlinear dimensional reduction for training sets of SPECT images and embedding the images into low-dimensional space using diffusion maps. Second is diagnosis. We provide a diagnosis procedure for every patient with 25-volt voting to predict and construct an interpretable two-model confusion matrices. Third is classification. The linear discriminant analysis LDA are used to the classifiers for diagnosis of early Parkinson's disease with diffusion maps reduced points. Three common images for diagnosis of Parkinson's disease include CT, SPECT, and fMRI. SPECT image is a radio-label drug is injected into the human body, and the gamma ray signal is collected from outside the body, and then cross-sectional image is formed by a computer. In this study, we use critical data sets of KCGMH-TW. The total of training data is 130 SPECT images and 100 SPECT images as testing sets. We take the middle base 3 slices of images by unclear medicine from the 9 slice SPECT as our research targets. Currently, the traditional diagnosis of PD is mainly based on doctors' visual diagnosis. So doctors spend too much time in SPECT diagnosis, and early Parkinson's disease is not easy to be diagnosed. In Manifold learning, the task of recovering meaningful low-dimensional structure hidden in high-dimensional data in many cases of interest, the observed data are found to lie on an embedded submanifold of the high-dimensional space. Different from equivalent distance, the geodetic distance between 2 points in the image are approximated by graph distance between 2 points. Thus, equivalent distance should not be used for approximating the distance between 2 points in nonlinear manifolds, where geodetic distance can be used. In this study, we firstly proposed the use of diffusion maps for dimensional reduction of the data, and then we compute the difference between SPECT image 128 by 128 by 128 by 3 pixels and brightness value in equivalent L2 known distance. Finally, the SPECT images are embedded in manifold trajectory. For illustration, let's an direct graph G in which V and E are the sets of vertices and edges, respectively, be defined that each node is connected by the weighted edge matrix W, such as figure 2. In diffusion map, the weight between node I and J is usually defined through the kernel function, such as Gaussian kernel with Wij, where K is positive and symmetric kernel matrix using division use equivalent distance, where the element of degree D is computed by summation of DII. And then we can construct a transition matrix P which normalizes row entry with unit length. The property of diffusion distance is timestamp of Markov transition matrix P. Pij denotes the transition probability Si from the points Sk in one time step. The denoted by probability Tsk computation Sj is the probability distribution of the random walk landing at the location Sk as time t. Given the definition of random walk on the graph, it's only natural to qualify the similarity between any 2 points according to the evaluation of probability distribution initialized as a delta function as these points. We can, in the division vector, let yi be the n by 1 distance vector with elements composed of distance from node I to all node j, j equal 1 to n, including itself made from the original data points I1 to the n named equation 6 and 7. We can use the spatial decomposition of P matrix to compute the right and left eigenvalues of P and denote by equation X, and then the coordinates of diffusion distance we can write as the cupcake eigenvectors between different two eigenvectors of P express the low-dimensional structure. Because of the recalculation of the kernel matrix with new added samples and the above steps are repeated for the entire data set, we can extend new sample points as new from the validation set and then recalculate the equivalent distance and the kernel matrix. The new elements of kernel matrix has an argument vector. So the argument Markov transition matrix Pn-1 can be rewritten as the equation 11 and 12. In our dimension reduction process shown in figure 3, each point of each patient is projected onto the origin trained low-dimensional division space and extended new sample to training space. Finally, we use the select classifier to carry out the classification. The main of our approach is two-step model diagnosis. For making cross-validation study, we split a total of origin data samples to normal and abnormal group. In first step, several manifold learning methods are used for dimension reduction on the training sets for low-dimensional embedding, and then our sample extension is applied to the new samples of the validation set. Next, classify the embedded samples and aggregate the example classifiers with 25-volt voting results to make prediction on the corresponding testing set. Second step, according to the results of the first step, we use the diffusion map and the classifier with the best performance to predict new testing samples. We implement the KCGMH-TW dataset with 3 SPECT images from 9x9 slides as a high-order brain image tensor as input to the 3D CNN. The classification results are reported in Table 2. The M-L method generally achieves the best performance on 2 datasets with single and 3 types. Compare our approach method, 2D CNN often have excellent prediction than 3D CNN, such that VG16 in PPMI is 93% and the DCN in KCGMH-TW is single image is 87%, but also has high variability. The comparison of our method, the M-L in PPMI single image and the KCGMH-TW 3 images classification has average accuracy 98% and 90% performance with lower variability. For overall, first, we will introduce the 2 model confusion matrices. First, we set the data label as true label, 2 classes, and the example DM and the LE diagnosis in 2 classes in figure A, and then check how many misclassifications under the true label, normal or abnormal. The diagonal elements of 2 model confusion matrix table are the numbers of correct predictions, positive with label 1, negative is with 0 for the DM and LE examples respectively. The number of misclassified samples are shown in the non-diagonal subtable. For example, in the left table in figure B, left column is true label of normal. DM and LE predict ID 678 is early abnormal. In right column, figure B, CT 177 is predicted by LE and abnormal is predicted incorrectly as normal by LE and correctly as abnormal by DM. Diagnosis table. Sometimes we care about false negative situation as 7 cases as indicated figure D. For this misclassification, we can provide more detailed information for data's diagnosis table and the probability of LDA matrix as demonstrated in Table 2 in order to identify early abnormal in true designation of this classification. We can also check if in our model prediction an error due to high age or shrinking situation abnormal for this situation. In conclusion, in visualization, we use DN for dimension reduction on 630 origin space image in low-dimensional space and visualize the embedding test sample in corresponding three-dimensional manifold uses three eigenvector 5, 1, 5, 2, and 5, 3 with largest three eigenvalue